Welcome back, class. This is Silvana. We are studying Living Systems 1, a core subject for Bachelor of Agriculture and Technology students. So welcome to week 2 of semester, and tonight's lecture is a very interesting one. So this is really where the chemistry starts, right here with what's called the periodic table of the elements. It's great. You never get sick of learning about the periodic table. And of course, when we're talking about elements and the periodic table, of course, we need to talk about atoms. And you can see a lovely representation down here of some atoms. And if you've never done chemistry before, you won't probably recognise that the C is for carbon, H is for hydrogen, O for oxygen, and so on and so on. But you will pick it up very quickly. So don't worry about it there. And you can also see here very nicely the relative sizes of these atoms of different elements. So not a bad place to start. All right, so let's get on with our lecture for tonight. All right, so we introduced the concept of an element last week. We know an element is a class of pure substances, but an element can't be broken down into simpler substances by a chemical reaction. We will see that each element is identified by a 1 or 2 letter symbol, and they are referred to as element symbols. Elements are all arranged in this great table called the periodic table of the elements. And what we'll come to see tonight is that the position of an element in that periodic table will actually tell us a great deal about its chemical properties. All right, so let's start with this table, which lists some of the common elements and their element symbols, which you were just introduced to on the actual first slide. All right, so let's look at them. Most of them are straightforward. So bromine is the element, and the actual element symbol is Br. So you can see that that's taken from the name bromine, and many of them are like that. Ca is the element symbol for calcium, C for carbon, Cl for chlorine, Cr for chromium. Then we've got cobalt, Cu for copper. That sounds like an odd one. So where does that Cu come from? F for fluorine, H for hydrogen, I for iodine. And here's another very odd one too, down the bottom, Pb for lead. Now, for those of you that have done chemistry, I'm going to keep testing you. So what does that Pb actually stand for, and where does it come from? I'm not sure if we've got anyone online tonight that's done chemistry, BCE chemistry. Any idea where that Pb comes from? And someone's dropped out. Pb for lead doesn't seem to originate, the element symbol doesn't seem to originate from the name lead. And that's because, I'll just grab my pen, that's because that Pb comes from, oh, you'll get used to my very messy writing, plumbum. Plumbum, that's an L there, Plu. So this is the Latin name for lead. So hence this odd Pb for lead. All right, we move on. Magnesium, Mg, manganese, Mn, molybdenum, Mo, nitrogen N, oxygen O, phosphorus P. Here's another odd one. It's also where we get plumber from. Oh, I've never heard that. All right, someone has just said it's also where we get plumber from. Okay, that sounds very interesting. All right, here's a good one that you should know, potassium. Potassium, K. So where does that K come from? Who can tell me? K for potassium. Ah, they keep dropping out. Does anyone know? Oh, Latin. Someone actually did answer my question earlier. Thank you. K for potassium. Okay, also Latin, kalium. Thank you. Good. All right, so when you see those odd element symbols, you can look them up and basically find out where they originate from. Now, another one that you need to know, another very important one, is sodium Na. All right, who can tell me where that Na comes from? Sodium Na. Natrium. Very good. Okay. All right, so that's one that you should remember. Natrium. There we go. Excellent. S for sulfur and Zn for zinc. So most of them are quite straightforward, easy to remember if you haven't done this before. All right, so let's clear that and get rid of that. All right, terrific. Here it is, the great periodic table of the elements. This one that you can see in front of you is not complete. It's taken from the original edition of your chemistry textbook, but that's fine. Excuse me. Still very, very useful to look at. So we can see that starting up here, we can see that each element is given a number. So H for hydrogen, and that's sitting at in the number 1 position. To find number 2, we jump across here. He is helium. Then to go to number 3, we're back here. Lithium, number 4, 5, 6, 7, 8, 9, 10, and so on. But of course, as some of you will know, these numbers are not simply just a numbering system. They actually tell us a great deal about the that particular element, and that's what we'll come to learn tonight. All right, but let's start firstly with these colours that you can see and what they mean on the periodic table. By the way, I won't be using this periodic table during Living Systems 1 and Living Systems 2. I'll show you the one that I want you to use in just a minute. And for good reason, because for students that have never done chemistry before, this table is not particularly useful in that it doesn't actually list the names of the elements. It just shows the element symbols. I'll come back to that in just a minute. All right, first thing to note is the colours. So let's start here down the bottom with the metals. So you can see that all these elements in green, these are referred to as the metals. In brown, we have the metalloids, and you can see they start here, and then we can step down, or roughly step down, across the periodic table here, and we have these metalloids. So you can also see, once you identify which ones are the metalloids, then you can say that everything to the left of the metalloids, or to the left side of the periodic table, is a metal, with one exception, and that exception is hydrogen, number 1. Hydrogen actually belongs to these elements in blue, or in other words known as the elements to the right side of the periodic table, or more specifically to the right of the metalloids, and those elements in blue are referred to as the non-metals. Okay, so keep that in mind. Hydrogen is the exception to that metal, the rule of the metals being situated to the left side of the periodic table. All right, let's look at another couple of interesting points here, must-know points. So firstly, each column in the periodic table that you can see here is given a number. And those numbers refer to each column as a group. So they're called group numbers, not column numbers. And you can see here that we have 2 sets of numbers. We've got 1A and 1. In other words, these are the group 1A elements, or the group 1 elements. We're only going to use this numbering system here, the 1A system. In other words, we've got group 1A elements here in the first column, group 2A here. Then we jump across the periodic table to group 3A. So we've got the group 3A elements, group 4A, 5A, 6A, 7A, through to 8A. All right. All right, so that's 1A to 8A. Now we come to these short columns in the middle of the periodic table. And the numbering system starts here, 1B, group 1B, group 2B, then back here, 3B, 4B, 5B, 6B, 7B, and then 8B covers these three groups or columns here. All right, so that's the first thing to remember, is what do we mean by a group? So remember, a group or a group number refers to a column of elements in the periodic table. Next thing to note is that the periodic table is divided also into rows, but we don't call them rows, we call them periods. So we'll write that there, periods. So we've got groups and periods, where periods are the rows. So for example, here's row 1 or period 1. It contains this element and this one here. So only 2 elements in period 1. Back over here, here's period 2, which contains these 2 elements, and then we jump across to these elements here. Period 3, 4, 5, 6, 7. Now, one thing I should point out here is that these elements down the bottom here actually belong in here, in this gap. But they don't actually, they're not placed there because they're not governed by the same properties that govern the elements belonging to these group numbers here. So there are no group numbers for these elements here. They do have period numbers, period 6 and 7, because they belong to these 2 periods or rows here, but they're certainly not governed by the properties that you'll learn when it comes to groups. All right, so very important trends that we can see on the periodic table, and you'll see where these come into play as we go through tonight's lecture. All right, so before we move on, here is the periodic table that I'd like you to use. There'll be a link to this on Moodle, so you can follow that link and get yourself a copy of this, print out a copy of this periodic table for yourself. And you can see that this one's much more useful in that it actually gives you not only the element symbol, so He, but also the name helium, so that those students that haven't done this before can start learning some of the names. By the way, no need to memorise anything. You will become very familiar just through the course of Living Systems 1 and 2 with the most relevant element symbols, the most relevant elements and their symbols. So certainly don't need to go and memorise everything. One other thing, it will be this particular copy of the periodic table that will be provided for you in the final exam for this subject. Okay, so make sure you keep this one handy and refer to this one whenever you can. All right, this particular periodic table is also not complete. So I've said earlier that there are 118 elements. So this one was obviously put together before a few of those elements were actually discovered or approved, actually. So the last 4 elements were actually approved only 3 to 4 years ago. They were all man-made, I'll have to say, not naturally occurring elements. So approximately the first 90 to 100 elements that you can see here are naturally occurring. The others are all synthesised in the lab. And the reason I can't be more precise is because there's still a lot of debate over some of the elements, whether they do occur in nature or whether they are just a matter of being synthesised, man-made elements. So that's why I say from 90 to 100. All right, let's get back to the lecture then. All right, so we saw that the elements in the periodic table are divided broadly into three groups: the metals, non-metals, and metalloids. So just some properties of the metals. They're located on the left side of the periodic table, more specifically to the left of the metalloids. They usually exist as shiny solids. They're good conductors of heat and electricity, and they are all solids at room temperature, except for one, mercury, and that's the element symbol for mercury, which is a liquid. Oh, sorry, we've got a question. Will this be provided in the exam? The answer to that is yes. Yes, the periodic table will be provided as an attachment to the final exam. All right, so one exception to this rule: mercury, Hg is the element symbol. All right, let's look at the non-metals. So these are located on the right side of the periodic table, more specifically to the right of the metalloids. Now, can anyone tell me which of the elements to the left of the periodic table belong to this group known as the non-metals? So remember that one exception that I spoke about. Hydrogen, correct. So remember, the non-metals, the group of non-metals to the right side of the periodic table also includes hydrogen, which is found to the left, far left of the periodic table. All right, so the non-metals normally don't have a shiny appearance. They're usually poor conductors, and they can be either solids, liquids, or gases at room temperature. That is, some are solids, some liquids, and some are gases at room temperature. And here's some examples, two examples of solids: sulfur and carbon, an example of a liquid, bromine, gases, of course, nitrogen and oxygen. Okay, and let me just skip back to the periodic table of the elements. So given that this is the copy that you will have in your final exam for this subject, just note that it doesn't indicate where the metals, metalloids and non-metals are. So you need to have that very clear in your mind. So when you're actually presented with this, you can immediately say, all right, I'm going to now mark or shade the metalloids, and then I'll know which are the non-metals and which are the metals. All right, so that's an important task for you to be able to do that going into the final exam. All right, and finally we have the metalloids, which are located on that solid line that starts at boron and then angles down towards astatine. The metalloids have properties intermediate between the metals and the non-metals, and they're represented by only 7 elements. Once again, there is still a little bit of debate around the metalloids, and they're listed here for you. All right, last week you were also introduced to this term, a compound, and a compound, of course, is also a class of pure substances, and compounds are formed by chemically combining 2 or more elements together. And of course, the compounds are very, very abundant because most of the elements don't actually exist in nature on their own as individual elements. More likely, they'll react with other elements to form compounds. All right, so we're going to talk very, very briefly about compounds because I want to focus on the elements, atoms and the elements. All right, so what do we mean by a chemical formula? Let's look at some examples first. Here's a simple chemical formula, H2O. Everyone knows that H2O is the chemical formula for 1 molecule of water. Here's another example on the right, C3H8. So this is also a chemical formula, and this particular one is for propane. So what are these chemical formulas? Well, they include element symbols such as H for hydrogen, O for oxygen, C for carbon. So they contain element symbols which show the identity of the elements involved in forming that compound. And they also use subscripts, which shows the number of atoms that are required to make up that compound. So in this example of water, so 1 water of molecule will contain 2 hydrogens and 1 oxygen. Okay, so where there's no subscript indicated, that will indicate that there is only one of that particular, one atom of that particular element present. All right, so that's water. Let's look at 1 molecule of propane. And everyone's probably familiar with propane. It's normally a gas, but it can be compressed to form a liquid. And if anyone had a barbecue today, that's possibly what was in your gas cylinder, your barbecue gas cylinder. All right, so 1 molecule of propane contains 3 carbons and 8 hydrogens. And they're all chemically joined together to form that 1 molecule. And the same applies to that 1 molecule of water. All right, you'll see if anyone is thinking of getting the textbook or even through these lectures, you'll see that compounds can be drawn in different ways. So we've just looked at this particular representation of 1 molecule of water, H2O. You might also see water drawn using this ball and stick representation, where a red sphere represents 1 oxygen and a white sphere represents a hydrogen. So you can see the 2 hydrogens there bonded to the oxygen, the red oxygen. You've also seen this representation. This is a space filling model, and we have individual molecules of water occupying this space. And because they're so far apart from each other, if I asked you this question, you would already know that represents water in the gaseous phase. In other words, water vapour. All right, and the different elements, as we said earlier, are represented by different colours. All right, so what are elements made of? Elements are composed, each element is composed of an atom. All matter is composed of the same building blocks called atoms. So when we think of the basic building block of all matter, we can think of the atom. If we were talking about living organisms, so plants, animals, depending on what you're studying, the basic building block of a living organism is the cell. Okay, but here we're talking about atoms. All right, so let's look at what atoms are made of. Atoms are composed of 1 or more, or most atoms anyway, are composed of 1 or more of these 3 subatomic particles. Here are the subatomic particles listed here in this table. So they are known as the proton, the neutron, and the electron. So an atom of each element is composed of 1 or more of these 3 subatomic particles. All right, the proton. We abbreviate the proton simply to a lowercase p. The neutron we abbreviate to a lowercase n, and the electron we use this abbreviation. We use a lowercase e with a little negative there. Okay, so keep those in mind for protons, neutrons, and electrons. All right, the proton carries a charge. Each proton carries a single positive charge, +1 charge. The neutron is neutral, as the name suggests, so the charge is 0. This particle, subatomic particle known as the electron, and you can probably guess just from looking at that, carries a negative charge. So we write that as a -1 charge. Okay, so these are all important concepts right here. Let's look at the mass of each of those subatomic particles in grams. And the masses are incredibly small, as you can see. So one proton has this mass, 1.6726 by 10 to the -24. If you were to convert that into a standard number, that would be a lot of zeros, which you would have to write in here before the 16726. And if you write this out, if you actually have a go and write this out as a standard number, you'll start to understand why scientific notation is so important, because writing out that number of zeros, we're prone to making mistakes. Okay, so that's the mass of a proton. The mass of a neutron is very, very similar, as you can see, 1.6749 by 10 to the -24. But the mass of an electron is even smaller, about 1,800 times smaller. 9.1 by 10 to the -28. Incredibly small. So small, in fact, that it's said to have negligible mass. Okay, so we discount that when we're working out the mass of a particular atom. All right, now because these numbers are a little bit difficult to work with, chemists actually came out with a standard measurement, a standard unit of mass. And that standard unit is called AMU. AMU stands for atomic mass units. So let's write that out. So this is one that you should know also, atomic mass units, AMU. There you go, my terrible writing. All right, so where did this standard come from? It was actually set at 1/12 the mass of a carbon atom. That's the standard, 1/12 of the mass of carbon. Okay, so that's the standard, and the masses of all the atoms of other elements are relative to this standard. So this is set at, AMU, 1 AMU. All right, so that means that one proton has a mass of 1 AMU, one neutron, it's almost identical, so it's said to have a mass of 1 AMU, but when it comes to electrons, we say they have no mass. Well, no mass that we're going to consider anyway. All right, let's clear that. All right, now let's look at what the atom actually looks like. Here we have the structure of an atom, just a generalised structure of an atom. Okay, so let's start with the actual centre of the atom. The centre of the atom is called the nucleus. Okay, the entire atom is found here. That's the very centre, and what we find in the centre, if we actually enlarge that nucleus, this is what we would see. Well, we would never see it. They can't actually see these. They do use very fancy experimental protocols to actually determine that they are there. All right, so within the actual nucleus itself, we can see in red are the neutrons. In blue are the protons, and you can see that they're given a positive charge for each of those blue protons. So this is what you would find within that small nucleus in the centre of an atom. So because this is the location of the protons and neutrons, and remember each proton weighs or has a mass of 1 AMU and each neutron has a mass of 1 AMU, this is where the location of most of the atom's mass is, right in the centre in that nucleus. All right, so what about the electrons? The electrons are found circulating in this, this cloud here called the electron cloud. The electrons are found here. So this electron cloud comprises most of the volume of an atom. So a great example is that if you imagine the MCG, imagine the MCG being the actual electron cloud itself, and one football sitting in the middle of the MCG would represent the actual nucleus. That gives you some idea of the size of the electron cloud relative to the actual nucleus of an atom itself. All right, now we're going to visit the periodic table again, now that you know about the atom and the subatomic particles within the atom. We're going to look at some really important numbers and start to learn what they actually mean. So once again, looking at the periodic table, and we can see we've got hydrogen with this number above it, number 1, and helium with that number 2, lithium with that number 3 just above it, and so on. So that number that sits directly above the element symbol, and here we have lithium with its number 3, that number is called the atomic number. Here's the abbreviation for atomic number, it is Z. What does that number tell us? That tells us the number of protons that are in the nucleus of an atom of that element. So in other words, a lithium atom has 3 protons in its nucleus. And every atom of lithium will have the same atomic number. Every atom of lithium will have the atomic number 3, which means that every atom of any given element will have the same number of protons in its nucleus. Let's look at that. So lithium, all atoms of lithium will have 3 protons. All atoms of hydrogen will contain 1 proton, and so on. All right, so we can see that different elements have different atomic numbers. In other words, they have a different number of protons. And in fact, it's the number of protons in the nucleus of an atom that determines the identity of the element. If you change the number of protons, you would change the identity of that element. Okay. All right, now a neutral atom, and we're going to only consider neutral atoms tonight. A neutral atom will have no net overall charge. No net overall charge. So that means the atomic number Z, while it's telling us just the number of protons, if it was a neutral atom, then that number of protons will be equal to the number of electrons. Okay, so that there is no net overall charge. Let's just talk about this just a little bit more. So if we just consider 3 protons, or rather the 3 positive charges that are associated with these 3 protons, and 3 electrons, or rather the 3 negative charges associated with those electrons, then we can see that the number of positive and negative charges are balanced. So the overall charge will equal 0. Okay, so that means we have a neutral atom. All right, that's a really important concept, particularly going into next week's lecture. All right, so remember, when you're asked for the number of protons and electrons for any element on the periodic table, all you need to do is look at the atomic number. And you know that will tell you the number of protons, and therefore in a neutral atom will also tell you the number of electrons. All right, now we're going to look at another important number on the periodic table and learn what that actually means. And that number is called the mass number. And here's the abbreviation A. So where do we find the mass number on the periodic table? that is the number that you see just under the element name. So for hydrogen, the mass number is 1.01. For carbon, it's 12.01, but we're going to focus on this one, chlorine. Chlorine has this number, 35.45. That's the mass number, or rather, when we round that number down to 35, we can treat it as the mass number. All right, let's go back. All right, what does it mean? The mass number A equals the number of protons plus the number of neutrons. In other words, that number 35 that we just looked at for chlorine, that is giving us both the number of protons and the number of neutrons in one atom of chlorine. All right, so let me get my pen and let's see what we've got for chlorine on the periodic table. So we just saw chlorine like that. We saw the atomic number sitting up here, number 17. And we saw the mass number, 35.45, but we just rounded that down to 35. And there's our mass number. All right, we're going to swap them around. Okay, we're going to swap them around so that the 35 is at the top. So in other words, as a superscript, and the 17 is down the bottom as a subscript. So this particular representation of chlorine enables us to work out the number of protons, number of neutrons, and number of electrons for an atom of any given element. Okay, and you'll come across some questions like this in the tutorial exercises for this week. All right, so this representation of chlorine puts the mass number A at the top and the atomic number Z at the bottom here. All right, so given this representation, when you're asked what are the number of protons in this particular, an atom of this element, you already know from the atomic number that it is 17 protons. Okay, given that it's a neutral atom, it's not charged in any way, you would also assume that the number of electrons is equal to the number of protons, that is 17. Then to work out the number of neutrons, this is where we look at the mass number, 35, and we simply say 35, take away the number of protons, 17. So 35 take away 17 gives us 18. So that means in one atom of chlorine, you will have 17 protons, 17 electrons, and 18 neutrons. Okay, does everyone follow that? Straightforward? Yes, excellent. All right, we'll look at, you'll see some more examples, as I said, in your tutorial questions. All right, but we won't leave this here. You might wonder, why did we go from, I'll just get rid of that. Why did we go from chlorine 35.45 down to 35? Why did we round that? What's that all about? All right, so 35, sorry, just get my pen again. So it was actually 35.45, but we just used the number 35. And that's because there are different types of chlorine. Here we looked at a type of chlorine called chlorine 35, okay? But there are different types of most of the elements on the periodic table, different types. And those different types are called isotopes. So isotopes are atoms of the same element that simply have a different number of neutrons. They still have the same number of protons because remember, if they didn't, they would no longer be that particular element, they would be something else. But the number of neutrons can change, and that the different atoms of the same element are just referred to as isotopes. So let's clear that and look at an example. All right. Here we have a great example. So carbon, this is how we see carbon on the periodic table. It's found at position number 6. In other words, it has the atomic number 6. And here is what's called the atomic mass, also referred to as the atomic weight. But if you want to be correct, you will say the atomic mass. But of course, as we said last week, we use these terms interchangeably. But as long as you know that they mean something a bit different, atomic mass. All right, atomic mass. Oh, there we go. Let's change that to atomic mass. But of course, you'll often hear me refer to atomic weight. All right, so carbon. So carbon, the most abundant type of carbon is this one here. C12, in other words, carbon 12. That's the most abundant. It forms 98.9% of all carbon on Earth. Here's another type, carbon 13, 1.1%, and a third type, carbon 14. This is a radioactive form of carbon, and you can see that it's not very abundant at all. All right, so what's the difference between these 3 isotopes of carbon? There's actually quite a few isotopes of carbon. These are the 3 most abundant. They differ in the number of neutrons that the atoms actually contain. All right, so this number that we see here, before we actually round it down or round it up, that is the atomic mass, is simply the average of the masses of the naturally occurring isotopes of a particular element. And it's reported in AMU, atomic mass units. So this number here is an average of the abundances of these 3 isotopes of carbon. All right, let's clear that. And let's go to an example of how to determine the atomic mass or atomic weight of a particular element. You don't need to do this, but this is simply so that you know how those particular numbers are calculated. All right, here's an example. What is the atomic mass or weight of chlorine? All right, firstly, we need to know what the different isotopes are. Here they are, chlorine 35, which we already looked at. And here's the other one, chlorine 37. So the mass of chlorine 35 is 34.97 atomic mass units. Chlorine 37 is obviously heavier. It has a mass of 36.97. Here are the isotopic abundances of the 2 isotopes. Those abundances are converted into fractions. All right, and then you simply multiply the isotopic abundance by the mass of each isotope and then add up the products. All right, so here are the... Okay, question, how are the abundances known? The abundances are actually known by samples, by testing samples. So obviously they couldn't test the abundance across the entire Earth, across the globe. So they actually take samples, and that's how they work out the abundances. So obviously they wouldn't be 100% accurate, but I'm certain that they would have done this for long enough that they have them fairly accurate. Good question. All right, do they change? Question is, do they change? Do the abundances change? Very good question. I couldn't tell you 100% the answer. I would say yes. I would say yes, that the abundances do change. And I think probably the best example of a dramatic change in abundance of a particular isotope would be when a meteor enters our atmosphere. Particularly if something actually landed on Earth, then you would say that that would be a very, very obvious change in abundance. Absolutely. But you could also think about something more relevant to your field of study. So if we think about elements in the soil, for example, can anyone think of how an element in the soil may change? Oh, sorry, how the abundance may change of an element in the soil? Especially thinking about global warming, climate change, runoff leaching. Okay, yeah, good ideas. But when we think about runoff and leaching, that's still all contained within the biosphere, isn't it? We actually haven't lost anything from our Earth and from the biosphere. Carbon mass. So we've got some good ideas coming through. Ploughing fields, carbon mass, salt, nutrient uptake, soil degradation from ploughing. Okay, so I'm thinking about all these great ideas, but I'm still not seeing how they would be lost from the Earth. Do you know what I mean? So yes, we're losing important nutrients from the soil in many different ways. Volatilisation, yes, all these are very, very good ideas, but how are they being lost from our biosphere? That's a really good question. One to really think about. Physically removed from the biosphere, like coal. Absorption or chemical reaction within the soil. Okay, so I'm thinking about that example of coal, burning coal. Yes, but are the emissions still contained within the atmosphere, or are they lost? Great ideas, everyone. Fantastic. Let's all look into this, shall we? Look into how elements can be lost from the Earth, but not just from the Earth, from the atmosphere. Let's think about how they can be lost. So think about maybe the ozone layer. Think about the hole in the ozone layer. Yep. Increase, yep, in temperature or pollution. Yeah, really great ideas coming through. Yeah, fantastic. Let's look at these ideas a little bit further, and let's come back next week and see if you can tell me what we do, what humans do to enable elements, important elements, to actually be lost, not just from the Earth, but from our atmosphere. That's great. Yep, great ideas. All right, I believe, yes, that the answer to the original question in that element abundance does change. Very, very, in very small amounts, but does change over time. Oh, here are some good ones coming through. Photo dissociation, yes. Waste helium in balloons, yes. You can see how that would cause a loss of particular elements from the biosphere. Yeah, great ideas, everyone. All right, let's come back with that next week. Come back with some solid evidence, yeah, as to how abundance changes over time. But you know, obviously the change in abundance would be very, very small, but nevertheless, over a significant period of time, you know, this can amount to something quite important. I mean, if you can just consider how the oxygen in the atmosphere, how that came to be over an enormous time span, that shows a very, very significant and critical change in abundance. Yeah. So, yeah. All right, where were we? All right, so multiply the isotopic abundance, which we can see here, by the mass of each of those two isotopes of chlorine, add them together, and what do we get? 35.45. Here it is here. And that is the number in AMU that we can see right here for chlorine, 35.45. So now you know where that number actually comes from. All right, as I said, you don't have to do this. Work out the atomic weight of an element based on isotopic abundance, but it's good to know. Good to know where those numbers actually come from. All right, let's now look at some more features of the periodic table. So we've already seen that each row in the periodic table is referred to as a period. In other words, period 1, period 2, and so on. And each column in the periodic table is referred to as a group. And we refer to those groups using group numbers such as 1A, 2A, 3A, and so on. All right, so more broad sort of groupings in the periodic table. So this one here is an important one, the main group elements. The main group elements consist of the two columns, or I should say the two groups on the far left of the periodic table, that is 1A, groups 1A and groups 2A, and then the 6 columns on the far right of the periodic table. And the groups are numbered 1A through to 8A. Let's look at them. So the main group elements are found here, main group elements here, and these ones over here. So groups 1A through to 8A. All right, then we have the transition metal elements. These are contained in the 10 short columns in the middle, and they're numbered 1B to 8B. We don't talk about these ones very often, or maybe a handful of them. And then we've got the inner transition elements, which consist of the lanthanides and actinides. And as we said earlier, there are no group numbers assigned to these, and that's why they're left out of the main part of the periodic table. And we never talk about these ones, not in the life sciences anyway. All right, and here they are for you. Main group elements are the ones in blue. So groups 1A, 2A, and these ones to the right. Then we have the transition metal elements, which are found here, and then the inner transition metal elements here. All right, some more features of the periodic table. And this time we're looking at some names that are given to the elements belonging to a particular group number. So all the elements, except for one, found in group A are referred to as the alkali metals. So who can tell me the exception to the metals rule in group 1A? What's the exception? Hydrogen, good. All right, so don't get tricked by that question in your tutorial questions. All right, all the group 1A elements are called alkali metals except for hydrogen. All right, group 2A are referred to as alkaline earth elements, and they all have similar properties: soft and shiny metals, low melting points, good conductors of heat and electricity, and they all react water to form basic solutions. Don't worry about that. We'll talk more about bases when we talk about acids and bases and pH in a later lecture. All right, this is an important one, group 7A. I want you to remember that group 7A elements are the halogens. And the reason that these are so important is because they are very relevant to studies in the life sciences. They are important because they are highly reactive. They combine with lots of other elements to form compounds. They exist in nature as two atoms joined together. All right, so really important group for halogens, group 7A. Let's look at them. Here they are over here, group 7A, fluorine, chlorine, bromine, iodine, and statine. Why are compounds called salts? Very good question. But first thing to note is that not all compounds are called salts. Only certain compounds are called salts. Any chemistry people, can any chemistry people tell me what is a salt? What is a salt? I'm sorry to put those chemistry people on the spot, but it's very good to revise. NaCl is one example of a salt, absolutely. But how do we define a salt? How do we define a salt? Yes, yeah, they are, but that's not how we define a salt. A salt is a product of a particular, that's the one, it's a product of a very specific type of chemical reaction. And someone has answered that, very good. It is formed, a salt is formed by a reaction between an acid and a base. It's the product formed as a result of a chemical reaction between an acid and a base. That's it. That's how we define a salt. Okay, but we'll talk more about that in a later lecture. All right, so 7A, Group 7A halogens, very important. Group 8A are the noble gases. These are not the only gases that you find on the periodic table, but these particular gases, the noble gases, are very, very stable. They rarely, if ever, combine with any other elements. They are so stable, and we'll understand later on why they're so stable. All right, so they're the noble gases. We don't talk about them very often in the life sciences. Oh, excuse me. All right, now we're going to look a little bit more closely at the electrons in the atom. So the electrons don't just whiz around freely within that electron cloud that surrounds the nucleus of an atom. They're confined to a specific region, and that gives that electron or those electrons a particular energy. It was taught for a long, long time that electrons actually circle the nucleus within their electron cloud. It's now thought that they don't actually circle the nucleus, they actually occupy a very discrete region within the electron cloud. But anyway, that's just me going off track. All right, the regions that are occupied by electrons within the electron cloud are called principal energy levels, or simply shells. And here's the abbreviation for a principal energy level for a shell. And the shells are numbered. N equals 1, 2, 3, and so on. So let's start looking or trying to visualize that. So let's say that's the nucleus of an atom, which contains, as you know now, contains the protons and the neutrons of that particular atom. And let's imagine that this was the first shell, the first principal energy level. That would be number 1. N equals 1. And then we could go out here. So this is N equals 2, the second shell. It's further out, it's bigger, as you can see. So it's going to hold, obviously, more electrons. Here's N equals 3. And so on and so on. So these electrons, the electrons that are found in the lower numbered shells, so in other words, any electrons found here, they're closer to the nucleus, they're held more tightly, and so they're said to be lower in energy. Why do you think they would be held tightly to the nucleus? Why would electrons here be held in some way to the nucleus, keeping in mind that electrons carry a negative charge? Because of the positive charge of the proton, correct. So remember, you've got protons in here that carry positive charges. So these electrons, these negatively charged electrons, are very close. So they are going to be attracted to the positive charges of the protons. And that holds them a little bit more tightly, and therefore they have less ability to move, so less energy. Whereas the electrons out here in the higher numbered shells, they're further away from the nucleus. The attraction between those electrons and the protons in the middle here are not as great. So they are said to have higher energy levels. All right, let me clear that and move on. So the shells with the larger numbers are further from the nucleus. You saw that they have a larger volume and can therefore hold more electrons. let's look at the distribution of electrons in the first 4 shells. So here's shell n equals 1. It can hold a maximum of 2 electrons. Shell number 2, n equals 2, can hold a maximum of 8. N equals 3 can hold a maximum of 18. And n equals 4, further away from the nucleus, increasing energy level as we move further out, can hold a maximum of 32 electrons. All right, here's where it starts to get a little bit confusing. So these are the bits and pieces that you need to go over until they become clear in your mind. So each shell is divided into 1 or more subshells. And the subshells are identified by these letters, S, P, D, F. So that's just something that you have to remember. S, P, D, F are the subshells. And each of those subshells consist of 1 or more orbitals, where an orbital is simply a region of space where the probability of finding an electron is high. Each orbital, regardless of which subshell you find it in, can only hold a maximum of 2 electrons. All right, so a good thing to remember here, once again, are the subshells, S, P, D, F, and then the number of orbitals in each one. Okay, so an S subshell, regardless of where it's found, that is regardless of which shell you find it in, only contains 1 orbital and therefore can only hold 2 electrons. Yep. All right, so 1 orbital, so only 2 electrons. 2 electrons. A p subshell, regardless of which shell you find it in, has 3 orbitals, so 3 by 2 is 6. So a p orbital can hold a maximum of 6 electrons. Okay, a D subshell has 5 orbitals, 5 twos are 10, can hold 10 electrons, and then an F subshell can hold 14 electrons. What about elements with a higher number of electrons? Oh yes, so you need to go further out with your shells and subshells, but we're not going to go there. We're going to keep it at this level right here. So you go further out with the shells, the shell numbers, and you go further with the subshells. It gets a lot more complicated than what we're learning here in our basic chemistry. All right, so hopefully everyone's clear with that so far. And we're going to look at some examples. So this table, it's a little bit difficult to follow, but it basically shows just the first 4 shells. As I said, that's all we really focus on. The subshells and the orbitals. So we have an S subshell here, denoted by that lowercase s in shell number 1. Okay, and as we said, an S subshell can only hold 2 electrons. All right, shell number 2 holds an S subshell and it holds a P subshell. So we see 3 P's here because there are 3 orbitals in a P subshell. Okay, S subshell, 2 electrons. A P subshell with its 3 orbitals can hold 6 electrons. So shell number 2 holds a maximum of 8 electrons. Shell number 3 has an S subshell and a P subshell and a D subshell. So remember S, P, D, F. Once again, S subshell holds only 1 orbital, therefore 2 electrons. P subshell has 3 orbitals for a total of 6 electrons, and a D has 5 orbitals for a total of 10 electrons. So the maximum number of electrons is 18. And then we go to shell number 4, an S, P, D, and an F subshell for a total of 32 electrons there. Okay. All right, so when you visualise that, here's our nucleus once again. Here's our n equals 1. It has an S subshell. Let's look at n equals 2. It has an S and it has a P. Oh, that should be a P subshell. If we looked at shell number 3, we would have an S, a P, and a D. S, P, and a D, and so on. Okay? All right, very briefly on orbital shapes. So they have determined that different orbitals have different shapes. So the S orbital simply has a spherical shape, which hasn't come out very well there. A P orbital has a dumbbell shape, and you can see an example there, and there, and there. So three orbitals in a P subshell, and here they are all together, drawn on the same set of axes. So they all have different shapes. You don't need to remember them. All right, more important is what's referred to as electron or electronic configuration. So the electron configuration describes how the electrons are actually arranged in the atom's orbitals. And the lowest energy arrangement, which is what you're going to be able to describe, is called the ground state. All right, so rule number 1, when you're asked to determine the electronic configuration, ground state electronic configuration of an atom, rule number 1, remember to place the electrons in the lowest energy orbital. In other words, beginning with shell number 1, S subshell. The orbitals are then filled in order of increasing energy. Okay, so that sounds straightforward. You'd start with 1s, and then you would move to placing electrons in the 2s subshell, and then if there were additional electrons that you needed to place, you would place them in the 2p subshell, and so on and so on. But there are a couple of exceptions to this rule, and here they are right here. All right, so when you're given a particular number of electrons and you need to place them into the shells and subshells, as I said, you would start here, lowest energy level 1s. Then you would move to 2s and then 2p. Then you would move out to 3s, 3p. But here's the tricky bit. Before moving to fill electrons in 3d, you would fill the electrons in the 4s subshell, then fill 3d, then go back to 4p. Okay, so it's out of order. Keep that in mind, it's out of order. And you can see that that's certainly the case elsewhere. And that's because of the different energy levels. Okay, so in this case, where we moved from 3p to 4s, that's because the 4s orbital is actually lower in energy than that 3d orbital. So it is filled first with electrons. All right, quite complex to actually work out why this is the case, and you would need to have a very good understanding of orbital shapes to really appreciate why that's the case. Okay, but we won't go into that detail. All right, I can also tell you that we don't go any higher than 4p. All right, so this is the only glitch, if you like, that you need to remember, that you would fill 4s before you fill electrons in the 3d subshell. All right, rule number 2, each orbital, as we said earlier, holds a maximum of 2 electrons. And rule number 3, we're going to discount, because rule number 3 applies to a particular a particular way of expressing electron configuration that we're not going to use. And I'll show you that in just a minute. All right, here we go. So this particular method of working out electron configurations uses orbital diagrams. That is, an orbital diagram uses a box, as you can see here, to represent each orbital, and then it uses arrows to represent electrons. So this is a single unpaired electron, and here are two electrons. So an electron pair with the arrows going in opposite directions. And that's called a paired spin. Now, we're not going to use this particular method of expressing electron configuration. That particular method uses orbital notation. So just for your interest and so that you're aware of it, we're going to use this method here, electron configuration. All right, so let's take some examples, work through some examples. But before we do, we're going to have a break, just a quick break. 5 minutes, is that enough for everyone? Yes. All right, terrific. Great. I will see you all in 5 minutes. All right. Hopefully everyone's back on. You have recharged your glasses or cups of tea. Yes, wonderful. All right, let's look at how to work out electron configuration for a given element. Let's start with hydrogen. Our favourite atomic number, Z equals 1, which tells you automatically that a hydrogen atom has one proton and therefore one electron in a neutral atom of hydrogen. You are being asked to draw or write the electron configuration for hydrogen. That means we need to place that one electron somewhere. Where do we start? Shell number 1, here it is, S subshell. And we write that one electron here as a superscript. And that's it. That's the electron configuration for hydrogen. Let's look at another example. Helium, atomic number Z equals 2. In other words, it has 2 protons and therefore 2 electrons in the neutral atom of helium. So we need to write the electron configuration for helium. That means we need to place those 2 electrons. Where do we place them? Shell 1, S subshell, 2 electrons are written as such. Remember that S subshell only has that one orbital, so it can only hold 2 electrons. So this is a completely filled subshell, completely filled shell and subshell. Another example, lithium has the atomic number Z equals 3. So that means it has 3 protons and therefore 3 electrons in a neutral atom of lithium. Let's actually write out the electron configuration for lithium. 1, shell 1, S subshell, it can hold 2 electrons only. 2 out of the 3 electrons can go there. Now we need to move into shell number 2. And we start with the S subshell and we place the 3rd electron there. So now we have a total of 3 electrons. That's what we want for lithium. So this is the electron configuration for lithium. Next one, carbon, atomic number Z equals 6. So a carbon atom has 6 protons, and therefore, if it's neutral, it also has 6 electrons. It is balanced. The charges are balanced. Let's place those 6 electrons into an electron configuration. Shell 1, S subshell, we can place only 2 electrons in there. Now we need to move into shell number 2, S subshell. We place another 2 electrons here. Now we need to move into the P subshell of shell number 2, and we place electrons 5 and 6 in here. Okay, so we have a total of 2, 4, 6 electrons, which is what we want for carbon, and here is the electron configuration for carbon. Let's try another one, neon, Z equals 10. So 10 protons and therefore 10 electrons, 1s2, 2s2, 2p. Now we move into P. We can place 6 electrons in the P subshell. That gives us a total of 10 electrons, and we now have the electron configuration for neon. Another example, and this is where you need to remember that little glitch in filling orbitals. Or placing electrons, we can say. So this element is calcium, Ca. According to the periodic table, calcium has 20 protons and therefore 20 electrons. So we have to place those 20 electrons. Let's look down here at the electron configuration. Yep. But before we do that, let's just go back. Let's go back here to this slide. So remember 1s, 2s, 2p, 3s, 3p. But if we still have more electrons to place, we need to fill 4s before we go to 3d. Now, keeping that in mind, we can place these 20 electrons. 1s2, 2s2, 2p6. Now we move to shell number 3, 3s2, 3p6. But now we go to 4, 4s2. Okay, so the 4s2 is filled before you would go to 3d, which we don't need to in this case because we now have a total of 20 electrons. So is everyone feeling more comfortable with electron configuration? Comfortable enough that you can go off later and complete your tutorial questions, which also happen to be assessed, this week's tutorial questions. Okay, have a go. Let me know how you go if you have any problems at all. All right, so another trend that we can see in the periodic table, and this relates to electron configurations. So we can see here that groups 1A and 2A, elements rather in groups 1A and 2A, are referred to, not very often, but can be referred to as the S block elements. And this is because the very last orbital to be filled with electrons for these elements is an S. It's an S subshell. Okay, so they're referred to as S block elements. Then we've got these ones here in the middle. They're called D block elements, because the very last subshell to be filled with electrons happens to be a D subshell. Of course, in a different shell, but it's still a D subshell. Here we have the P block elements, and down here we have the F block elements. Okay, not particularly useful, but you do have one tutorial question that will relate to this particular slide. All right, something much more important is the concept of valence electrons. So when we talk about the chemistry of any element, of any atom, of any element, the subatomic particle that really determines the chemistry is the electron. The electrons determine the chemistry of any element. So the chemical properties of an element will depend on the most loosely held electrons, which are found in the outermost shell, the most loosely held electrons, which also happen to be the electrons that have the highest energy level. Though that outermost shell that actually contains electrons is called the valence shell. Okay. Those electrons that are found in that valence shell are called valence electrons. All right, let's have a look at some examples here. So here we have the electron configuration for beryllium, which happens to be 1s2, 2s2. So the outermost shell, that is the valence shell, is shell number 2, n equals 2. The valence electrons are those electrons in the outermost shell, and we can see that there are 2 there. Okay, so we have 2 valence electrons in this particular atom. Let's look at this example. This is the electron configuration for chlorine. What is the outermost shell? That is the valence shell for chlorine. It is shell n equals 3. How many valence electrons does this chlorine atom have? Well, we simply look at the number of electrons in the valence shell. There are 2 there, and there are 5 there, so we have a total of 7 valence electrons. Elements in the same group number on the periodic table will have similar electron configurations. Elements in the same group will have the same number of valence electrons. So this is a really quick and easy way to determine how many valence electrons a particular atom of a particular element has without working out the electron configuration. How? You simply look at the group number itself. Not in every case, there's always exceptions to every rule, both in chemistry, biology, biochemistry, and so on. But the group number, in general, the group number, particularly group 1A to 8A, will equal the number of valence electrons for the elements found in that group. There's one exception to that particular rule. The exception is helium. Helium is found in group 8A, but it doesn't have 8 valence electrons, unlike the others. It only has 2 valence electrons. But generally, elements in group 1A will have 1 valence electron. Elements in group 2A will have 2 valence electrons, and so on. The chemical properties of the elements in a particular group are very similar because those elements contain a similar electron configuration, particularly of those valence electrons, which happen to be the most reactive electrons for a given atom. All right, so that's just shown here that in group 1A, these elements have 1 valence electron. Group 2A, 2 valence electrons that you can see here. So only the actual valence shell and valence electrons are shown in these electron configurations. And so on through to 8A, but remember, for the 8A elements, the noble gases, helium is an exception to this rule. It does not have 8 valence electrons, unlike the other noble gases. Okay, we have a question. Does the 3D subshell electron get considered as a valence electron when it is in shell number 4? That is a very good question. Does a 3D subshell electron get considered as a valence electron in shell number 4? The answer to that is no, it doesn't. Here we have another question. Is it the valence electrons that combine with other elements to create compounds? Yes, it is. Absolutely. And we will talk a lot more about that in lectures next week. In fact, next week and the week after. So very important concept, the valence electrons. All right, now we're just going to look at a representation of valence electrons, and this is referred to as an electron dot symbol. So you'll be required to be able to draw electron dot symbols, and if you have a good understanding of these concepts that we've been learning, then this will be fairly straightforward for you, very straightforward in fact. Although there is an interesting one that students tend to make a lot of mistakes with, and I still haven't worked out why, but it's a common error that I see year after year. But anyway, maybe one day I'll work that out. All right, what is an electron dot symbol? So firstly, we use dots to represent the valence electrons, and those dots are placed on the 4 sides of an element symbol. So each dot represents 1 valence electron. When there's only 1 to 4 valence electrons that need to be placed, then just single dots are used. When there's more than 4 valence electrons, then the dots are paired. So let's look at some examples. Hydrogen. It has 1 valence electron. In fact, it only has 1 electron in total. All right, so what do? You're asked to draw an electron dot symbol. So you draw the element symbol, hydrogen, and then you place a dot next to it, as you can see here, and that's the electron dot symbol for hydrogen. Let's look at another example. Carbon has 4 valence electrons. How would we know that very quickly? By looking at the periodic table, that carbon has 4 valence electrons. Oh, let me just, okay, carbon. All right, find carbon on the periodic table and tell me how you would know very quickly that carbon has 4 valence electrons, not not the total number of electrons in carbon, but just group 4A. Excellent. All right, don't forget, here's carbon here. So we know it has 6 protons and therefore 6 electrons in total, but it has 4 valence electrons. We know that just by looking at the group number 4A. Okay, good. Keep that one in mind. That's a really good one to use. All right, just going back now, and let's draw carbon. Electron dot symbol carbon. We have to place 4 electrons. So we go 1, 2, 3, 4. Why are the dots? We have a question. Why are the dots on a particular side of the letter? It doesn't matter what side you place them on. You can put them anywhere you like. Okay. All right. Next example. Oxygen. This is the one that students tend to get very confused with. Oxygen. All right. Let's have a look at the periodic table. Oxygen. And we can see oxygen is here. It belongs to group 6A, which tells you immediately it has 6 valence electrons that you need to place. All right, so let's do that. Oxygen. 1, 2, I always start from that side. I don't know why. It doesn't matter what side you start from. 4, now we start to pair them up. 5 and 6. And you'll see in later lectures why I pair them up like this. All right, there's our 6 valence electrons, which is what you have here. All right, and then we have chlorine. Let's look at chlorine on the periodic table. And here it is here, chlorine. Okay, it belongs to group 7A. It's a halogen, so it has 7 valence electrons. And let's go back here. Chlorine, so we write chlorine. There we go. 1, 2, 3, 4. Oh, not a good dot. 5, 6, and 7. Sorry, that should be a single dot there, but you can see it much nicer there. All right, so that's how you draw an electron dot symbol. Is that very straightforward for everyone? Don't make a mistake with oxygen. We'll see what happens. All right, we're nearly there, nearly there. So another trend that we can see on the periodic table, and it relates to the size of atoms, the size of atoms of specific elements, so atomic size. The size of atoms tends to increase as you go down a column. So if you were to start up here, for example, as you go down, the atoms of those elements get larger and larger. And that's because the valence electrons become further away from the nucleus. Okay, the size of atoms decreases as you go from left to right across a row, or a period, I should say. That's because the number of protons in the nucleus increases. And as the number of protons in the nucleus increases, they can pull the electrons closer to the nucleus, and that makes the atoms smaller in size. All right, so that's one trend, and then we have a last one here, and this is an important one relating to what's called ionisation energy. And we'll talk a lot more about this next week and the week after, but ionisation energy is simply the energy needed to remove an electron from a neutral atom. The energy needed to remove an electron. All right, here's a great example. This is sodium, Na, sodium. If we were to remove an electron from sodium, then the number of positive protons and the number of negative electrons would no longer be balanced, would they? They wouldn't be balanced. There would be a positive proton that no longer has that counteracting or balancing negative electron. So that means that that sodium would actually have an overall charge of +1, or simply a single positive. Okay, because as I said, you've removed a negative electron, so one of the protons in that atom of sodium no longer has a balancing electron. So it's overall it's charged, it's carrying a charge. And we write that lost electron as plus an electron. Okay, so that's really just introducing you here to the concept of charged atoms. All right, so once again, ionisation energy, the energy needed to remove an electron. And we can see this trend here that ionisation energies decrease as we go down a column, and that's because the valence electrons get further away from the positively charged nucleus. As they get further away, they're easier to actually remove, and hence the decrease in ionisation energy. Ionisation energy increases as you go from left to right across any particular period. And that's because the number of protons in the nucleus increases. If the number of protons in the nucleus increases, then they can exert a greater pull on those on the electrons. So you need more energy, greater ionisation energy to remove the electrons. All right, and that completes our lecture on atoms and the periodic table. So as I said, I'll put a link to this periodic table on Moodle, so you can print a copy or more than one copy if you like for yourself. Here are the tutorial questions based on tonight's lecture. You might have seen these already. These ones are assessed just like the questions from last week. They are due next Monday at by 6 p.m. And of course the quiz will close then. Assessment weighting 4%. Okay, so that quiz should now be open, but of course you can also find these questions in the tutorials folder on Moodle. So you can print them out if you like, or just save them and work through them before you actually attempt the online quiz. And also remember, all assessed online quizzes, you can have 2 attempts at the quiz. That is, you can complete 1 attempt, submit, get your mark, and then at any time you can go back to it. Well, that is any time before the quiz closes, you can go back to it and have a second attempt, which means that you should probably keep track of any questions that you get wrong as you go through in your first attempt, so that you know what to really focus on. Maybe do a bit of revision before you have another go. Okay, as I said, I was really pleased to see that most students, only a handful of students in fact, did not complete the first set of tutorial questions, which is really good, very good, excellent. All right, now, where are we? We are in week 2 of semester. So we're sitting here. Next week, we resume normal classes, so face-to-face and Zoom online. Here we go. There's your tutorial, set of tutorial questions that's due next Monday evening. So that's it for tonight. Oh, also, I nearly forgot. Now, for those students that have signed up for weekly prac classes, please don't forget that your prac classes will start next week. Okay, you'll have your first lab class next week. So in order to participate, you need to have a lab coat. How's everyone going with getting lab coats? All right, these here are 2 places where you can actually get your lab coats from. So don't forget to get your lab coat organised before next Monday if you are doing weekly prac classes. Those students that are doing the 2-day prac intensive workshop, you still have a bit more time to organise that. All right, and that's it for tonight. And we have an early finish. How's everyone going? Are you still with me? Thank you, everyone. I will see you all next week. Thank you very much and good night. Ciao. Thank you for letting me drink whiskey during class. Oh, very good. And here I was thinking that everyone's drinking wine, beer, tea, coffee. Someone was actually drinking whiskey. That's not fair. Is that fair? I suppose I really could be drinking and no one would know, would they? Good night, everyone.